high pH and high calcium content. So this is how we are currently disposing acid waste. So what we came up with, can we create circular systems for, instead of dumping down our in the drain and affecting the environment, can we create a circular food system? Okay, so we took the acid waste, we mixed it with millets. So once we mix it with millets, it has to go through a filtration process, a spray drying process, and so we could get powders, and then that powder could be used in any potential food application as a functional ingredient, and then other industrial applications. So that's how we were thinking of creating a circular economy. So this is how we did it in the lab. We had the acid waste, we had the millets, it goes through a filtration unit. Spray drying is another unit operation where we could control the time, temperature to develop fine millet form, like, powder formulation, the instant uh, powders and so on. And what are the health benefits for this, right? So we wanted to see, okay, what this is unique. The acid base has certain components, millet has certain health benefits. So we did a lot of color analysis, like LABs, chroma, whiteness index. And then we wanted to study the nutritional profiles of it, like proximate analysis, sugar profiles, amino acid profiles, mineral profiles, antioxidant profiles. So then we could understand what is the nutrition composition, and then connect it with the health component of, like, because it had, millets do have a high health benefits related to cardiovascular health, gut health, and because of its low glycemic index, it can also be used as a food for diabetes. So we were able to develop multiple formulations of this as a functional food, infant formula, whitening agent, as a mineral fortification. So that's how. So that's the overview of the methodologies and our results that we got. And if someone is interested, I can go through the results as well briefly to talk about. Since it's a department of physics, I would say, like, the moisture content was quite low, and the water activity, that's the amount that indicates the microorganisms that could be present in the flour, the powders, so that it could reduce the shelf life of the product. And the yield also was quite about 50%, which is pretty good. And that led to our the best formulation. These are all different formulations, so we were able to select a good formulation. And from our carbohydrates profile, quite high, as well as proteins was also good. But here, one thing that we wanted to share is the ash content. The mineral content was quite high in all the formulations that had the mix of both acid base and millets. And as you see, once we saw the protein profile was pretty good, we wanted to go in deep and see what's the essential amino acids. So essential amino acids are required by the body. So you can see certain quite high profiles of essential amino acids in the mix, and few in the mixed formulations as well, which was pretty good. Like, it had a synergistic effect. And as I said, the mineral content was also quite high. So we could have high amounts of calcium, zinc, copper, and so on. So both the micro minerals as well as the macro minerals, it was a good profile, indicating it could become a good mineral fortificant. And we wanted to see the surface morphology. So we did some analysis to see what is the surface morphology of it. Pretty much there was more smooth, indicating properties of encapsulating, and there was a little bit of agglomeration. That's quite common in powders. So that was pretty good. And then from the lab scale, where we were able to develop like 50 grams, 10 grams to 50 grams, we were able to scale up to at least 50 kgs of the same material. So the scaling up potentials of this project was also pretty good. So through this, once we developed a high amount of formulations, you can see this powder could be used in n number of applications, right? From anything whitening, we could use, like in pharmaceuticals and food applications and so on. And there are some metrics that we show here, how we can take a waste material and add value to it. And through that, like, not only contribute to the upcycling of the waste, but also contributing SDGs like zero hunger, clean water, because of the environmental issues that the acid waves causing, industry and innovation, creating new innovations and new startups based on the inventions that were developed through this very big nutritional disorder. And it affects more than 50% of women. In India, if you meet two Indian women, one might most probably be anemic, and that's a big challenge. So, as I said, right, India is one of the countries that's worst affected by anemia, and the government of India is taking a lot of initiatives to address this, which is really welcoming, because around 50% of women of reproductive age are anemic, and 70% of children are anemic. It's one of the highest records in the world, and the Indian GDP is reduced by 6% because of iron deficiency anemia. So you might be thinking, how such, like, no, it's a big challenge. So the vehicle that we selected for this was salt. You might ask, why salt, right? Salt is consumed at regular intervals. Unlike sugar, you can have an overdose of sugar, but salt you can only take a limited amount. You cannot over, like, consume a lot of salt. And irrespective of the socio-economic status, religion, region, gender, uh, salt is consumed by everyone. And also, the success of iodization of salt is also a very big success story throughout the world. And it's a centrally produced, and that's why salt was selected as a vehicle. And in this particular project, how we came through is, you can see this is ferrous fumarate, right? It, after extrusion and cutting into size of 300 to 700 microns, you will see this is how it gets agglomerated. Then we coat it with white color, because if I put something like this in a salt packet, no one is going to consume it. They will think it's an impurity. So that's why we had to code it, and we had to make sure also encapsulated, micro encapsulated, so that there will be less interaction between the iron and iodine that we're adding. Okay, so then mix them together to form a premix, and this is how the double fortified salt looks like. So this is all for the iron premix making, and this is for the iodized salt making, um, and you blend them to form the double fortified salt. Okay, so this is how the process flow for this whole project. You can see here, this is, I was talking, right? If we don't encapsulate them clearly, then there will be interactions. Is because this is an electron microscope of the iron premix. You can see how porous this material is, right? This is the iron. If And we are going to introduce this into a salt matrix, and that is also going to have iodine in it. So then there will be an oxidation of iodine, and like the sublimation of iodine, and it sublimes. So that's why we didn't want to have this. So we had to encapsulate it to form a smoother surface, to reduce the surface area and reduce the pores, so that moisture cannot enter it and prevent that interaction between iron and iodine. So these are some of the products that, like, after 6 months of storage at both 25 degrees Celsius and accelerated temperature of 45 degrees Celsius at a higher relative humidity, the salt performed quite well. So that's pretty good. You might be like, you'd have been seeing Tata double fortified salt, right? I hope.
Yes, ma'am. Yes. Yeah.
Yes. So these were the pre experiments that led to double fortification salt in Tata. So I'll tell you how all these things came together. So this project, initially it started, there were multiple stakeholders involved in this project. Okay, I'm just giving a brief overview. So we had universities in both. Sorry. So we had University of Toronto, we had the Delhi University, and multiple, University of Zurich, and like Cornell, McGill. There were multi-university project that validated the controlled trials and so on to say that this product was pretty good. Then we had food industries, like salt manufacturers in Gujarat, and then JVS in Jaipur. So some of they were premix makers, salt producers, so they were all connected. And then we had funding agencies, right? International NGOs like the Gates Foundation. GAIN is Global Alliance for Improved Nutrition, is a like Switzerland-based organization. So they all came together. And then we had Tata Trust. Tata, our local NGOs, and Tata has been one of the pioneers in this area who have been quite supportive, right, of this initiative. The Tata Trust was involved. And then we had the government of India. Government of India did, when in 2009, 2016, I suppose, 15 and 16. So that's when they mandated that fortification of salt becomes a big, a double fortified salt gets into the midday meal system and the Anganwadi system. So the government made the policies in place. And then we had international partners from Canada and the US. So you can see multiple people came together, and initially the trials, actually the preliminary trials happened in Tamil Nadu, but first pilot trial happened in Uttar Pradesh, and we were targeting few districts and reaching 24 million people. So that was the target. But then after its success, within a year, you can see the impact. Currently, it's other states are also implementing it, and currently it's reaching more than 60 million people, 60 million, 60 plus million people in India. So you can see that's the power of food and innovation, right? Because we all eat food. And whenever we start addressing one issue, we wanted to address issues of iron deficiency anemia and food. So we started with just SDG 2 and SDG 3, right? On this whole journey of doing it, it connected with gender equality, right? It connected with climate action. It connected with life below water. It connected with multiple, like life on land and partnership for goals. So multiple SDGs came together, and that's the beauty of SDGs, I feel, and transdisciplinary collaborations, because we cannot achieve individual SDGs alone. You need partnership to achieve that, so we can reach millions of people and create that impact. And another reason why we were able to reach so many millions of people is because we all eat, right? We are everyone. I hope you all had it's evening there, so you had lunch and looking forward to the dinner. So that's a very powerful connector, right? And that is why during the pandemic we saw such big disruptions. Like when the pandemic hit, it not only affected health, was a big significant factor, but it touched on multiple SDGs, right? From hunger, and then education, quality of education. Since the educational institution, there was disruption. There was clean water was even not available for drinking, whereas hand washing, right? So where multiple SDGs were impacted, and COVID brought to limelight that interconnected relationships exist between different systems, and we need more like a transdisciplinary approach. And so that we can create a system that is more transparent, equitable, and resilient. And so that's why, in order to address the zero hunger, we need to have all the SDGs together. This is a very beautiful report from the FAO. So if anyone is interested, I would highly recommend that. And to more sustainable and circular food systems. And partnership is key to success in the 21st century. And we have a good team here at Mizzou, and all the funding agencies who have helped us, our collaborators, who have supported our ideas and funded our projects. Feel free to reach out to us. And I heard there are around 100 students in this. But I would like to conclude with the amazing quote with Dr. Albert Einstein. Imagination is more important than knowledge, because knowledge is limited. Imagination encircles the world. So if you can imagine something to solve a SDG problem or a global problem, go for it, because we just have um, only one planet that we call as home. Okay. Thank you so much for this opportunity.